So the goal of this section is to do trigonometry on the unit circle, but to do that correctly we need to remind ourselves how to do trigonometry on a simple right triangle. So we're going to start by reviewing material from Sec 4 Mathematics. So we'll start with on a right triangle before moving on in the next video to trigonometry on the unit circle. So if I have a right triangle or right angled triangle, and this is theta in angle, this is 90 degrees here, I'm going to label this side here as H for hypotenuse, this side here as O for opposite side of the angle, and this side as A for adjacent side. Okay, so maybe H stands for hypotenuse, O is opposite, and A is adjacent side. Adjacent means just next to it. Okay. So by definition, the sine of theta is the opposite side over the hypotenuse. The cosine of theta is the adjacent side over the hypotenuse, and tangent is opposite over hypotenuse. We also have that these three sides satisfy the Pythagorean identity because they're part of those sides are part of a right triangle. So Pythagorean identity or theorem. So I write THM for theorem all the time, but I'm going to write it fully here. So we have that A squared plus O squared is equal to H squared. So that sort of summarizes everything we need to know on for trigonometry on the triangle. But I'd like to add something though. If this is angle alpha here, okay, the complement, okay, so this is the complement because alpha and theta are going to add up to 90 degrees. So complement of theta, okay, complementary angle. I should actually not complement, but complementary of theta, okay. So that's because theta plus alpha add up to 90 degrees or pi over 2. Okay. If I look at the sine of alpha, just for fun, sine of alpha, now the roles are interchanged because the opposite side of alpha is now A and the adjacent side is now O. So the hypotenuse stays the same, however. So the opposite side of alpha is A and hypotenuse doesn't change. Cos of alpha is adjacent over hypotenuse, but the adjacent side to alpha is O now. And tangent would be A over O. But I want to look at specifically sine and cosine of alpha, and notice that A over H was before the cosine of theta, and this before was the sine of theta. Okay. Now, because of that the angles theta and alpha add up to 90 degrees, which is what I wrote here, this is equivalent, what I wrote here is also equivalent to saying that alpha is pi over 2 minus theta, or it's in degrees, it would be 90 degrees minus theta. So if we replace alpha by pi over 2 minus theta, or 90 degrees minus theta, we get that sine of pi over 2 minus theta is the cosine of theta. We also get that the cosine of pi over 2 minus theta is the sine. So this sort of explains why we say sine and cosine. Cosine is the sort of the it's the actually we should look at this identity. If I look at this identity here, cosine, which is here, it's the sine of the complementary. Okay, So this is why it's the cosine. So the comes from complementary. Okay, so looking at this identity, we can understand why they chose the words sine and cosine. Again, because sine is the cosine is the sine of the complementary angle. So just a quick note, just to mention why we say sine and cosine. And let's look at an example where we have an angle of theta, and we've got two sides, and what we'd like to figure out are the values of sine, cosine, and tangent. Okay, so find sine of theta, cos of theta, and tangent of theta. So how do we do this? Well, for this we need to know what all the sides are equal to, because all those expressions here are ratios of the sides. So we're missing a side, so we're missing h here. So first thing is to use the Pythagorean identity to find what h is. So now we have that h squared is 4 squared plus 3 squared. So that's 16 plus 9, which is 25. So therefore h, which is a positive quantity, is going to be equal to 5. Okay. Now I know that h squared equals 25 as two solutions, plus or minus 5, but we disregard the minus 5 here since we're looking for a side of positive length. Now, sine of theta, having found this, that h is 5, now sine is just opposite over hypotenuse. Cosine is simply adjacent over hypotenuse, while tangent is opposite over adjacent. So we'll look at two more examples where we're going to find the missing side. Sides with a plural if there's more than one side missing. So first example, got 9x15. Okay, so try to do that one, pause and come back. Now this is a simple application of the Pythagorean identity. So 15 squared, the hypotenuse squared is the sum of the squares of the opposite and adjacent side. Well, there's no angle here, so it's kind of weird to talk about the opposite or adjacent. I could just say the two legs of the triangle, like that. Okay, so 225, which is 15 squared minus 81, is x squared, and x is going to be squared is going to be 144. So x is plus or minus 12, but of course we'd only keep the positive value of x here. So in B is an example where we have two sides missing, but we know all the angles in a triangle. So for example, this one's 70, and it's pretty easy to figure out that the missing one would be 20. Okay, so in fact we've got all the angles here, but we're missing two sides. So try to do that one on your own if you can. Pause and come back. Now, here I can't use the Pythagorean identity because I would have like two unknowns, h and a. So I'm going to use some information about sine and cosine. So, first of all, I can use the 70-degree angle. Okay, and notice I know the opposite side. Okay, so the sine would be opposite over hypotenuse. So using sine allows me to have an equality with only one unknown, so I can solve this for h. Notice if I would have used cosine, I'm sort of in trouble, because with cosine it would have been a over h, and now I've got a single equation with two unknowns. So this is why I decided to use sine and not cosine. Now solving this for h gives me that h is 2 over sine of 70 degrees. Now, if you don't know how to evaluate sine of 70 degrees with a calculator, in particular, angles in the calculator can be set in degrees or radians. If you don't know how to do that, which is probably the case, since maybe you haven't done, well, maybe with angles it's okay, but with radians. Eventually, I'm going to put a link on how to use the calculator to evaluate sine, cosines of angles that are either in degrees or in radians. So look for a link for that video on the Moodle page if necessary. So 2 over sine 70, so if I type that into my calculator, I'm going to get approximately 2.13. Okay, so this is the value of h. Okay, 2.13. Now at this point, to find a, I have two options. I could use a trig function again, just like I did for just now, to find the value of h, to find the value of a. But also now that I have two sides, I could use also the Pythagorean identity. So it's really up to you. But I'll show you here, maybe using another identity. If I use tangent, you see, if I use tangent, the tangent is opposite over adjacent. So it naturally leads me to an equation where I have a single unknown. Of course, now I could have used also, I could have used cosine, because now I know what h is. So both, that would have worked too. So a will be 2 over tangent of 70 degrees, and using my calculator, this is going to be approximately, so make sure you put your approximation symbol. We get 0.73. Okay, so this is 0.73. Just a quick check, your hypotenuse should always be greater than the two other sides. Okay, so if you find an hypotenuse that's less than the two other sides, something went wrong. So I guess we're done here. We found h and a as required. So now we're going to move to trigonometry on the unit circle.